So for the last part of this day, we're going to have Liam talking about latest updates in the folded schemes world. So yeah, thanks, Liam.
Hi. Okay. Thanks for coming to my talk. I'll be talking about recent advances in folding schemes, specifically Protostar and Protogalaxy, and how the folding works there. And so start out motivating folding, then sort of a simple example, and depending how it goes, maybe some more details. So just to start out, what is a SNARK? We have a circuit that encodes an NP relation, and we want to prove that we know some input to the circuit that satisfies it. So you could imagine that we just send the input to the verifier. The prover wants to convince the verifier, and that we can do better than that with a SNARK. We can prove that we know a W succinctly and non-interactively. So we can send much less information to the verifier than the total W, and we don't have to talk to them at all. We just produce a proof, send it to them. SNARK stands for Succinct Non-Interactive Argument of Knowledge, so succinct and non-interactive. Lots of different SNARK protocols that you probably are familiar with, Groth 16, Marlin, Planck, STARKs, and so on. But all of these are monolithic SNARKs, meaning that you have one witness and you produce one proof and just send it to the verifier. But SNARKs can also be used recursively because they're non-interactive. If you take the verifier circuit, like the program that actually the verifier would run, you can encode it into the circuit and then put a proof into the witness. And then if you prove the satisfiability of that circuit, that proves that you've verified a proof inside of a SNARK. And so you can use SNARKs recursively. This is a pretty powerful idea and is sort of generically sufficient to construct incrementally verifiable computation, proof-carrying data, and to distribute and parallelize the proving of SNARKs amongst multiple people and over time. So, just to define the terms, incrementally verifiable computation is when you have long-running computation and you want to prove it as you go. And so with a recursive SNARK, you can prove one bit of it, and then in the next bit, you prove that you proved the previous bit and prove the next bit, and so on. PCD is very similar, except instead of in a line, you prove in a kind of DAG. So you might have multiple proofs that you verify in each step. And so these are examples of parallel and distributed proving. And I mean, you can even use this to just optimize proving a monolithic SNARK. You don't need multiple people or to be doing it over time if you just want to spread it over multiple computers at the same time and so on. And this is how a lot of people who have production systems do it now. But encoding the verifier in the circuit can be very expensive. Depending on the proof system, it may not even be possible. For example, with bulletproofs, the verifier might have a bigger circuit than the circuit you're proving. And so that's obviously not going to work if you try and recurse. So what can we do? Well, maybe we don't have to verify the whole proof every time we recurse. Maybe we can fold multiple proofs into one new kind of composite proof so that when we finally verify the new folded proof, we can check that all of the input proofs were valid. So that is, if the X prime, W prime is valid, then all of the inputs are valid. And it should be the case that we can check that we folded much more efficiently than we could check the individual proofs. And so if we had such a protocol, then in order to do, say, IVC or PCD, you could prove each step, and then rather than proving the verifier for the previous step, you just fold the next step into some accumulator. And you maintain this accumulator of proofs, and then at the very end, you do the expensive verification. So this is kind of why folding schemes are interesting and what they're trying to do. So Folding schemes were introduced a couple of years ago in Nova for rank 1 constraint systems, just an arithmetization for circuits. And since then, there's been a ton of work extending the folding schemes to different kinds of arithmetizations like Plonk, and to fold lookup arguments, and to fold multiple R1CSs. So for example, if you had a processor and multiple instructions, you might want to fold different operations in each step. And so that's what non-uniform IVC allows you to do. It's been extended to CCS, which is like R1CS, but with high degree gates, essentially, in Hypernova. And then more recently, and what we'll be talking about today, it was generalized much, much more in Protostar to fold arbitrary polynomial verifiers. So in all the previous examples, the verifier computation or the decider computation had to be structured in some sort of way. So R1CS or Plonk or CCS. And in Protostar, it's sort of the maximal generalization of that, where you're just verifying that you're running a single polynomial, the verifier is. And then in Protogalaxy, joint work of myself and Ariel Gabizon, we extend Protostar to fold multiple instances. So that's, the field is continuing to progress. And so maybe you've heard of Nova, and you're wondering, like, what is the difference between Nova style and Protostar style folding? So in Nova style folding, so that would be like Nova, Supernova, Hypernova, each time the prover proves a new instance, they run the sum check protocol. The sum check protocol is old and recently had a big resurgence. But in order to do that, you use log n hash functions in executing the sum check protocol. And so in verifying the folding verifier also checks log n hash functions. And this type of folding, in order to use sum check, requires certain sort of structure to the statement that you're proving. And CCS is kind of like just a superset of all of the different ways that this could work. And it lends itself well to certain kinds of SNARKs based on how the sum check protocol works, like Spartan, which also uses a sum check for R1CS and could be generalized to CCS. So in contrast, Protostar and Protogalaxy do not use sum check in this way. They're just going to take any degree D polynomial map that maps some input vector to an output vector and fold it. And so the number of random oracle queries does not depend on the number of constraints here. Here n is like the number of rows in your R1CS. So just to set up kind of the details of how Protostar works, we're going to have our polynomial f, which is of degree d, and a homomorphic commitment scheme. And that means that if you add the commitments, then it adds the committed witnesses. So we'll let omega be a witness, just a bunch of field elements, and phi be a commitment to that witness. And we say that the witness is, or the instance is valid if it's a member of the relation, which is defined there. Just f is going to be 0 on the witness. So yeah, very, very general. We want to fold 2 of these, but first, maybe it would help to make concrete some of the generality. So we know that we can fold any f, but like, what's an example of an f that people might be interested in? So we have an R1CS instance, say, and we have 3 matrices, and we want to show that, if you multiply the matrices by the witness and then multiply component-wise, it all checks out. We can just write a function like that, which takes the witness, and for each row, checks that the R1CS equation holds, and that's it. Given that function, you can apply Protostar and Protogalaxy to it. Do the same thing for CCS, where instead of having just this degree 2 thing, we might have some sort of polynomial gate G that you evaluate over a bunch of different matrix multiplications. And so yeah, if it helps, you can keep this in mind as like an example F. So what do folding schemes do? Like why are they able to avoid running the verifier? The answer is they exploit the linearity of the commitment scheme in a really fundamental way. So as like a simple example, imagine that the prover wants to convince the verifier that some commitment phi prime is a linear combination of these witnesses. They could send the linear combination of the witnesses or the witnesses themselves, and the verifier computes the linear combination. But exploiting the linearity of the commitment, you can just simplify that expression and write it as a linear combination of commitments, which the verifier can check in time independent of the size of omega. Right? So the goal of a folding scheme is that we want to be able to verify a folding independent of the size of omega in some sense. And this is sort of the essence of how that works. That's why the folding verifier doesn't depend on M. It's also why it doesn't work with Fry, because Fry is not a homomorphic commitment scheme. So how do we use this to actually construct a folding scheme? So this is a pretty common technique, actually. It's not unique to Protostar, and it probably predates all of this work and just comes from math. But you can construct a line between our two witnesses. Remember, we're trying to fold two instances with omega 0 and omega 1. And then, by linearity, we can construct a kind of commitment to that linear combination of witnesses. And so if you evaluate omega at any particular x, you evaluate phi at any particular x, then phi at that value will be a commitment to omega at that value. So now that we have this kind of like line interpolating the witnesses, how do we fold? Well, what happens when we evaluate f, our big polynomial on the line? If you evaluate it at 0, then you can see that the second term cancels, and we're just left with f of omega. And if you evaluate it at 1, the first term cancels, and we're left with f of omega 1. So what we need to do is check that f of omega is equal to this kind of expression. You can see the same sort of property holds on the right-hand side. If we evaluate at x equals 0, you're left with f of omega 0, and if you evaluate at x equals 1, you're left with f of omega 1. And so if there exists some q such that this equation holds, then we can simplify it first. But if some q exists, then we know that f of omega 0 is what we claimed it to be, and f of omega 1 is what we claimed it to be by simplifying even further. Right? So each of those two terms should vanish, and we're just left with this quotient. So if a quotient exists, then both of the instances were valid. And this is the sort of folding claim that we're interested in. We want to be able to check one thing and then extract that the previous two instances were valid. So to do that, you just standard techniques, right? You can evaluate at a random value, evaluate our omega and our phi at gamma, but there's a problem because f of omega of gamma is not 0. So omega prime and phi prime is not a valid instance because we're left with this like error term. The solution we can use is to relax the relation to allow an error term. So instead of checking that f is equal to 0, we check that f is equal to a particular error term. And if we verify the error term is constructed correctly, then we can verify that the folding was done correctly. So here we can just define the error term like that. And easy to see that we have a valid, relaxed, randomized instance. So now, in this example, we folded two regular instances, but how would we fold if there were two randomized instances? Well, now we have two error terms, so we're going to do pretty much exactly the same thing we did before, construct the lines, construct a line through the error terms. Now what happens when we evaluate f? We're going to get the error terms, and plugging all that back in, we can see that now, instead of these terms vanishing, they'll be multiplied by the error terms. And so we obtain a valid randomized instance from two input randomized instances. So, I think one important thing to take away here is the algebra is pretty straightforward. It's nothing really crazy is going on. You're you're doing just evaluating f on a line and then checking that it evaluates to what it's supposed to evaluate to. So now we can get into some of the details of how Protostar is done sort of efficiently. Here, you'll notice that f outputs a vector. So each of these error terms is a vector. But we don't want to send a vector of error terms to the verifier because that's of size n. We'd also prefer not to send a commitment to the error terms. So, can we just make it a scalar, say? And it turns out that we can. If we take a random linear combination of the f's by powers of beta, then you'll see that if the random linear combination is 0, then it follows that f is 0 on that input. And in the case of a randomized instance, if we take the random linear combination of the error terms, then we are left with only a scalar. But how do we fold this new kind of thing? We've added this beta, and beta seems like it has high degree, so maybe that's a problem. It turns out that we can fold beta in much the same way we fold omega, by properly sort of redefining f and including beta as part of the instance. So just generally, both Protostar and Protogalaxy do this, but they do it in different ways. So we'll define just some vector, beta bold, and some family of polynomials g that outputs the powers of beta. So in Protostar, we're going to have beta vector be 2 vectors of length square root n, and then g will take one element from the first vector and one element from the second vector and multiply them to get beta to the I. In Protogalaxy, we have log n scalars, and each gi will take some subset of those scalars and multiply them to get a beta to the I. And so you can see, like in Protogalaxy, you just take the bit decomposition of I and multiply the different betas to the 2i, or to two powers, and so on. And so when we fold, these g polynomials are polynomials. They're both polynomials of relatively small degree, 2 or log n. And so in principle, we can do more or less the same thing we did before, right? You have 2 randomized instances with 2 different betas, and we want to linearly interpolate between them and then compute the error terms from g. G's are just more polynomials. So at least in principle, it seems like it should work. With a little bit of work, you can show that you can actually do this in linear time in the number of constraints, which might not be obvious in the Protogalaxy case because each of these GIs is going to be of degree log n. So if you want to compute n degree log n polynomials, that's maybe not obviously possible in O of n time, but it is. And just a note that these sort of lie on this spectrum of things where you can, instead of, they're sort of extreme versions, right? So like in the Protostar case, you could imagine 3 vectors of length cube root of n, or in the Protogalaxy case, you can imagine increasing the length of each of these log n vectors. And so, anyway. So we've described how to fold 2 instances and 2 accumulators, but what if we wanted to fold multiple instances and multiple accumulators? Well, this straightforward generalization, we just let z, so in the case of 2 accumulators, we're going to have z be this vanishing polynomial, which is just 0 when x is 0 or x is 1. And in that special case, x and 1 minus x are the Lagrange polynomials of z. If we want to fold k instances, then we can use a different z and just use the Lagrange polynomials for that z. And the previous equation where we were evaluating on a line, now we'll evaluate on a degree k minus 1 polynomial. And if you think about how the Lagrange polynomials are defined, for each root of z, and each Lagrange polynomial will be 0 except for one of them. So if you evaluate on each root of z, the left-hand side, all the terms in the sum will vanish. And on the right-hand side, all the terms but 1 in the sum will vanish. And you'll be left with exactly the same sort of equation we had before, where you evaluated at 0 and evaluated at 1. Yeah. And so Protostar is also sort of a general compiler for special sound protocols into folding schemes. So what I've described so far is like a kind of particular view of a folding scheme, but it's very easy to add multiple rounds of interaction between the prover and the verifier. So one reason you might want to do this is to do like a lookup argument. And so a lookup argument, like a log derivative lookup or lookup or any lookup argument, is going to require some randomness from the verifier. And so you'll need rounds of interaction in the instance that you're folding. And so the way this basically works is the prover is going to send some messages and get some challenges from the verifier. And this is, fairly simple, and then we're going to evaluate our f over all of it. It'll evaluate over the challenges and over the messages, and you just have some algebraic verifier that you want to check. So if we do this, we can just define the witness to be all the messages and all the challenges, and we can add the challenges to the instance and apply Protostar directly to this. Everything works the same as before, more or less. Plus, the verifier has to check that the challenges were computed correctly. So the one important caveat here is that in order to instantiate a folding scheme, you have to instantiate your random oracle because the verifier has to prove the execution or check the execution of the random oracle, which is not sort of possible for random oracles generally. But that's the case for all folding schemes that are in use, like Nova and Protostar. So now maybe just talk about some stuff that I haven't addressed, and if you're interested, definitely check out the papers. Or I did another talk for PSE that had maybe some more detail. But there are some significant benefits to using these general polynomials. So they're clearly powerful enough to encode structured computations, but you can also very easily modify them to do lookups, to do non-uniform circuits. So supernova, for example, does non-uniform IVC. You can just sort of do that with Protostar in the way you'd hope, where your prover work does not depend on the total number of operations, only the operation that you're folding each time. Then another big question in practice is, how do you actually compute the error terms? I just sort of assumed that we could, but it's maybe not obvious how. And so in general, if f is just some arbitrary degree d polynomial, it's going to be huge and impossible to work with. So in practice, f is almost always very structured. Even if it isn't so structured that it would fit into CCS, it's definitely structured enough that we can take advantage of it. So for example, it might have mostly low degree constraints, which you can take advantage of. And it might be written as a composition, maybe not of a linear function, but just a composition in general. And you can use that to, compute the error terms more efficiently. And then finally, in the Protogalaxy paper, we describe how to fold using sum check over the instances instead of Lagrange polynomials. And the big advantage here is that we're able to avoid FFTs and have sort of get rid of most of the log factors in the prover time. Note, this is not the same thing that Hypernova and Nova style protocols do. We're doing sum check to combine instances as opposed to sum check to reduce vector matrix multiplications. But anyway, sum check appears once again. And yeah, I think that's pretty much it. Any questions?
Thanks, Liam. So yeah, you asked the question. Any question? Come on, don't be afraid.
I think I would maybe just ask, where do you see the research maybe going from here in terms of, it's come a long way in the last 3 or 4 years. What are the things that still need to be tackled? What needs to be better and stuff like that, in your opinion?
I think that a lot of these protocols need to be implemented and then benchmarked and compared. That's kind of lagged the research, which makes sense given how fast it's moved. In terms of open questions, folding layered circuits, so like GKR, if there's a possibility to sort of fold that more efficiently than kind of the straightforward way. Yeah, I guess also exploring this like error term computation space, like what was the best way to do that, and these sorts of things. Yeah, I think those are the big new directions.
Sorry, also maybe a more foundational theoretical question I'm not aware of, but what is the soundness of the folding scheme depend on? So like, what is the assumption that you use? It's not like, is it informational theoretic? Is it just Zipple, or do you use some cryptographic assumptions?
So the main like different cryptographic assumption from a standard SNARK is this instantiating the random oracle. So you have to instantiate the random oracle as a hash function. And this is just a heuristic kind of argument. There are works that attempt to get around this, but they're sort of more theoretical on like, arithmetized random oracles. But the assumptions, I think, will mostly come down to the commitment scheme that you use. So if you use KZG or Pedersen, I suppose you could probably do something with groups of unknown order, but typically it's KZG or Pedersen because they have to be linear commitments, so you can't use Fry. So it would be like discrete log.
That's on this step where the folding scheme is still viewed as an interactive process before you fetch a mirror.
Mm-hmm.
Okay. And what about, so the folding scheme itself is not zero knowledge, right? So the error, so the error, there's like nothing that hides anything there at all.
Definitely.
So it also applies to your case.
That's maybe another answer to the previous question is adding zero knowledge to folding schemes. It's not like impossible. It's just, I think, something that probably needs to be done explicitly. Yeah, like Protostar and Protogalaxy don't deal with zero knowledge at all.
Okay, if that's it. Round of applause for Liam. Thanks.